In a world bound by the innate desire for self preservation, businesses and companies often opt to invest in technologies suitable for marketing and profit, leaving behind the pursuits of academic and scientific interest. As such is the case with Bell Labs, pioneering the research for day to day technologies such as telephones, lasers, transistors, solar cells, etc., gives opportunity for those interested in the realm of material science and condensed matter physics. Along with the rise of transistors and smaller computers, and the entrance to a new millennium, one popular field of study was supposed to be a promising opportunity to scientists at the time: organic semiconductors. Silicon based materials are most commonly used for semiconductors because they are relatively cheap, stable under operating conditions, and the process of doping these offers some room to customize their electronic properties. What makes organic semiconductors appealing compared to their inorganic incarnations? Well, organic semiconductors offer one, very customizable electronic properties, which surpass that of their organic counterparts. Two, they are even easier to process for large scale production, which makes them far cheaper to make. Three, they can be used for stretchable and bendable applications that inorganics can only dream of. And finally, four, they hold the promise of being able to further downsize transistors, continuing the reign of Moore's Law. But here's the catch: organic semiconductors are very sensitive to humidity, oxidation, and temperature. Not to mention, their comparatively lower charge carrier mobility means limited high speed electronics applications. These limitations that prevent organics from completely replacing inorganics is what is known as the organic barrier. What if, during a time of great economic strife for tech and telecommunication companies, a ray of hope in the realm of organic semiconductors suddenly appears, promising the dawn of a new age of computing? It wouldn't be surprising if everyone desperately clung to it, desperately wanting it to be true. And that's exactly what happened in the years 2000 to 2002. But it turns out that this was all false hope built on the lies and fabrications of one man, Jan Hendrik Shon. This tale follows his tragedy. Our story begins in the University of Constance in Germany. Shun attended the university and he received the equivalent of a combination of bachelor's and master's degree in physics, with specialization in electronics, in 1993, after which he was recruited for an internship at Bell Labs, which persisted from January to May of 1997. He went back to Constance to finish his PhD and subsequently went back to work at Bell Labs in September of 1998. In 2000, the dot-com bubble burst, leading to the telecom crash of 2001. As many telecom companies relied on dot-com success for clients and income, this financial turmoil forced tech and telecom companies into dire straits, with many filing for bankruptcy or laying off massive numbers of employees. Among surviving telecom companies was Lucent Technologies, which owned Bell Labs. This once knowledge-focused lab faced pressure to prioritize profitable research to avoid dissolution. Not all lab work was publishable or profitable, so for Shun to secure his job and become a full-time employee, he needed to produce revolutionary research or develop marketable products. This led to his February 2000 paper, Ambipolar Pentacene Field Effect, Transistors and Inverters, where he claimed to have broken the organic barrier by demonstrating the viability of pentacene and transistors, purportedly rivaling silicon. This landed Shun a permanent job at Bell Labs in December of that year. Since his employment terms had changed, he had to return to Germany once more in order to renew his visa, a process that took over 5 months. For that duration, he was working for Bell Labs remotely. His success in that paper, combined with his remote working setup, away from the prying eyes of his associates, created the ideal environment which began a chain of research that would comprise his body of fabricated knowledge on organics. In fact, his deception was so effective that he even won several awards, cash, and a reputation of a rising star in the field. Among his awards were the Outstanding Young Investigator Award worth $5,000 from the Materials Research Society Spring Meeting, the William L. Macmillan Prize worth $2,500. He, along with his co-authors Bertram Batlogg and Kristen Klock, also jointly received the $10,000 Industrial Award at the International Conference on Science and Technology of Synthetic Metals, as well as the Braunschweig Award worth $60,000. Science mentioned a molecular transistor paper of Shon's as part of their Breakthrough of the Year for 2001. He also made MIT's list of innovators under 35. But everything went downhill when some of Shon's coworkers noticed something strange in his work. Julius Su and Lin Lu, who were actually co-workers with Shon at Bell Labs, originally noticed problems, realizing that Shon had duplicated some numbers, presumably because they are affiliated with each other and that they were using his paper while attempting to patent research concerning lithography. This suspicion did not persist. Lydia's son, who was affiliated with Princeton University at the time, noticed that two experiments carried out at very different temperatures had identical noise. Paul McEwen of Cornell University found the same noise in a paper describing a third experiment. More research by McEwen, Son, Lu, and other physicists revealed a number of examples of duplicate data in Shon's work. This caused Lucent Technologies to start a formal investigation. During May 2002, Bell Labs established a committee to investigate. They obtained information from all of Shon's co-authors and interviewed the three principal co-authors, Zhenan Bao, Bertrand Batlogg, and Christian Klopp. This community also requested copies of the raw data but found that Shon had kept no laboratory notebooks. His raw data files had been erased from his computer. In the report of the formal investigation of the allegations, it said that physical measurements of the significant devices underlying papers in question were carried out by Shon alone. No laboratory records were systematically maintained, and all primary electronic data files were deleted by Hendrik Shon. It's also worth noting that all figures in the papers in question were, with one exception, processed and prepared also by Shon alone. In the end, the investigation concluded that, at a minimum, Shon showed reckless disregard for the sanctity of data in the value system of science. Shon did not follow generally established practice in his field about the maintenance of verifiable records, nor did he maintain original data in a way that crucial physical statements could be verified or even examined. As a result, it is impossible to validate or disprove the fundamental physical claims in the papers in question. Shon employed several tactics to sustain his fabrications. He often used relative units and graphs, avoiding exact values to make falsification harder to detect. When questioned, he exploited confirmation bias by adjusting data to meet expectations. His submissions to journals rarely changed, typically including the phrase, "Further experiments will be needed," to gloss over vague results, and he frequently claimed that any ambiguities would be clarified in forthcoming papers. So what can we learn from this? Shon teaches us how to falsify data and how to get caught doing it, because the truth persists. Because of how academia is built on the scientific method, the scandal teaches us a lot about the importance of integrity and careful record-keeping in scientific research. It shows how crucial it is to keep clear and accurate records to ensure results can be trusted and replicated. Shon managed to fake his data for a while without being caught, which points out the need for a strong peer review process and a healthy dose of skepticism, even for exciting new discoveries. The case also highlights how external pressures like economic downturns can influence research priorities and ethical choices. In a field dedicated to uncovering the truth, maintaining high ethical standards and promoting a culture of integrity are essential. This situation reminds us that while the temptation for quick success and recognition is real, the long-term credibility of science relies on transparency, honesty, and a careful checking of results.